Hey everybody, in this last video for this part we're going to look at the phenomenon of dispersion. So with the geometric laws that we have established, we can address this phenomenon. So what do we mean by the dispersion of light? Well, I think the classic example that you guys probably have seen is a prism dispersing light, right? So generally what we mean is that light is broken up into its constituent frequencies or colors. And again, the classic example is if I take a prism, and often the prisms are triangular, often they're equilateral triangles. So that might be a triangle of glass or plastic. And if we have white light coming in, a beam of white light, something like that, now we know that pure white light is a combination of all the visible frequencies. But when people were experimenting and noticing rainbows formed by the dispersion of light, because often when light goes through a window or right through water drops to form a rainbow, the light disperses and people see these beautiful colors, right? In fact, that's why we say Roy G. Biv, the colors of the rainbow. When people did these experiments, they didn't really know exactly what was going on. In fact, I'll talk more about that in a little bit. But they were able to do the experiments, controlled experiments. Okay, so when that combination of all the colors of the rainbow, that white beam hits the prism, we know that exiting the other side of the prism will be this rainbow, right? And I'll indicate that in a little bit, but what's the cause of that? Let's talk about that. Well, it turns out, I haven't been lying to you, but I haven't really told you the entire truth. The index of refraction for a material is a function of the frequency. It is not a constant. So n is a function of frequency is not a constant. Each frequency of light has its own index of refraction for that material. Now, the variation can be relatively small, so that's a less dispersive material, or relatively large, a more dispersive material. The values of the index for like a typical piece of glass, the values changing out in the thousandths place, maybe the hundredth place for a strongly dispersive material. So numerically it's not a huge effect, but physically it is, because and mathematically because of the nature of the sine function. Okay, so the next thing I want to establish is, and what you guys should know a little bit about, is normal dispersion, because most materials will exhibit what we call normal dispersion over a certain frequency range. And our focus is going to be over the visible range. So I'm going to make a sketch here for a given material. This is the index on the vertical axis. And instead of plotting frequency, I'm going to plot it versus versus free space wavelength. Often, again, we like to plot things versus wavelength or examine the wavelength, the free space wavelength, rather than the frequency. Again, I think it's just that predilection for visualizing the wavelength. Okay, so if I make a plot of n versus the free space wavelength, and again, I'm not going to put numbers on here, but we want to get the sense of large or smaller. Where is the red portion of the spectrum on my horizontal axis? Is it over on the left or over on the right on the horizontal, right? So what I'm asking is, red light, does that have a larger free space wavelength than violet light? And the answer is yes. You guys should remember that, right? You're Roy G. Biv. So red's going to be over here, and then violet, well, I'll just choose blue instead of hunting for a violet. So, but just pretend my blue is violet. So violet's going to be down here. And again, the orange, yellow, green, blue are going to fill in from right to left. So if I make a sketch then of what would normal dispersion look like, what does the index look like as a function of free space wavelength? It's going to be something like that. It's going to be a curve. It's not linear. although over maybe a very small portion of wavelength, you might approximate it as being linear. But over the visible wavelength is going to be this curve. In fact, this is known as the Koshi Formula. Often what people will fit this to is a constant, I'll call it A, plus another constant over the free space wavelength squared. Okay, so that's often done in optics as a fit to that dispersion curve. Okay, now, if we look at Snell's law, because that's what we want to focus on to explain the dispersiveness of the material, the fact that the light gets broken into its different frequencies or colors. We have N1 sine theta 1 equals N2 sine theta 2. So let's look at the first interface. This is my white light beam, so all the frequencies are together there. If I were to draw the surface normal for that first interface, it would be like that. You guys see it's perpendicular to that triangular side of the prism. So this is the angle from the surface normal to the ray. That's going to be theta 1. Okay, so now we have to look at the refracted ray, theta 2, the angle theta 2. Now remember, N red, I'll do it like that, is less than N violet. So let's just look at the two extremes, red and violet. For normal dispersion, N red is less than N violet. Mathematically, right, the left side of my equation is the same for the different frequencies. But N red is smaller than N violet. So to keep this as an equality, I need what? I need sine theta red compared to sine theta violet. What do I need? Well, N red is less than N violet, so sine theta red better be bigger than sine theta violet. And the nature of the sine function means that theta red is bigger than theta violet. Okay, so that's the math. So what does that mean in my picture? What's that physically what's happening? Well, if I were to draw that, the red angle's got to be bigger than the violet. So let me start off with my violet. Now this light is going from air into a piece of glass or plastic. So it's going from low into high. I remember that means it's going to bend towards the normal. Okay, so I'm going to make, instead of going straight across, it's going to bend like this. That would be my theta violet. That would be this angle right here, that tiny angle there. Theta red's got to be bigger than that. So if I were to draw my red ray, it's also going to bend towards the surface normal. Whoops. Okay, but it's not going to go straight across. It's going to go like that. You see this angle right here has got to be bigger than that violet angle. Okay, another way to remember this, for some reason I remember this. It's really not a great mnemonic, but a professor that I had one time told me this. It's blue bends more. Blue bends more. There's a little bit of alliteration with the blue and the bends. Blue bends more, violet, meaning more than red. And then you can throw in violet bends most. I don't know if that helps you or not. But violet bends more than red. Okay? So in my picture then, what happens? And remember, all the other colors are going to be between those two extremes. So you're going to get this rainbow forming, right? This rainbow wedge, if you will, forming in the prism. Now, if we keep track of these separated colors, this red ray is going to come and hit here. Now, that's just one frequency. So if we look at the refraction now, because here's a new interface, right, tilted like this, the other side of the triangle. For this interface, this would be the surface normal. And this is going to bend away from the normal, right? Because now we're in a high index going into a low index. So this is going to bend away from the normal. So it's going to bend something like this, like that. And then if you trace that blue ray, which it's really violet, okay, so if I come over here and find my violet ray, it's going to come down straight. As long as it's in the same material, it's going to be traveling straight. And then it's going to also refract away from the normal. So it's going to go like that. And what you have then exiting is you have this rainbow exiting. And those are not parallel. The red and the violet are not parallel. That rainbow is going to be diverging. So it's going to be spreading out. Okay, so that's the classic refraction occurring in a prism. And I want you to remember blue bends more. Okay? Now, I mentioned when people first were playing with these prisms, they didn't really know exactly what was going on. So they could produce this rainbow. Oops. They could produce this rainbow right here, but they really didn't know what was going on. And in fact, people thought at the time that they were doing these experiments. Now, this is the time around when Newton's around this time. People thought that the colors of the light were stored in the prism, and somehow the sunlight was stimulating the glass to produce these colors. One of the things that Newton gets credit for is he showed that no, the colors are already in that white light. And he did a very simple thing. What he did is he took two prisms. So the first prism dispersed the light in this rainbow fashion. What he then did is he took another prism and he said, well, I'm going to put another prism right here, like so. I'll put this one upside down like that. And lo and behold, when these dispersed colors hit this second prism, everything was put into reverse. If you follow the refractions, these different rays are going to refract, and when they exit, they will exit all on top of one another, and you get the white light beam back. So Newton was showing that, look, the colors can't be stored in the glass, because when this light enters the second prism, right, it should cause more colors to come out. That you shouldn't get white light back out. All right, so what he was showing is that the first prism is actually dispersing the colors that were already in the light beam, spatially dispersing them, and then the second prism is refracting them, putting them back together on top of one another to give you white light. Okay, and you guys may be aware that there is a classic album cover, Pink Floyd's Dark Side of the Moon. This is the front of the album cover, and that was it. There was no writing on the front, so just showing the classic prism experiment. But what's cool is on the back of the album, I'll show you right here. Okay, so this is the album cover unfolded. I should say the album sleeve unfolded. So the front is on the right and the back is on the left. So it folds in the middle. So you see the classic experiment, okay? And it's continuous if you notice, right? Now, physically, right, there'd be some absorption of light, so this could not be going on forever. Plus, where's the light source coming from, right? But it's a cool album cover and a classic one. Okay, one other thing about dispersion. I mentioned rainbows forming in water droplets, and here's a picture. This is a cute little cartoon, but oh, can I make it bigger? Yeah, I can make it bigger. Okay. All right. So what happens is in a water droplet, if you look at the sun, now the sun's shining light in all directions. Just focus on the top drop. These drops are really, really, really tiny. So essentially there's going to be, quote, one ray of light hitting the drop, right? So here comes the sunlight. Let's say it's traveling to the right. it's going to refract and disperse. Remember, blue bends more, violet bends the most. So you're going to get the red ray on top here and the violet ray on the bottom. Then, when these rays hit this droplet, if this is one of the drops that's forming the rainbow, you actually get total internal reflection right here. It's pretty cool. Okay? So then, if you look at these rays, trace them, they're going to go straight through the water, and then each of these is going to refract out into the air again. And realize, right, they're going from high index into low index, so they're all going to bend away from the normal. So coming out of one drop, you have the violet on the top and the red on the bottom. But if you've ever looked at a rainbow, right, the primary rainbow has red on the top and violet on the bottom. Well, that's because it takes many layers of drops, vertical layers of drops, to actually form the entire rainbow. If you look at your eye, right, your eye, the pupil of your eye is an extremely small aperture. So from one drop, you essentially are getting just, again, in our stripped down geometric optics model, you're getting one ray from each droplet, if you will. Okay, and if you just look at the pure geometry, all of the rays coming from the different layers, they have to enter that small pupil. Well, if you do the ray trace, that means the drop giving you the red ray, that red ray will always be on top. So if this guy's seeing the rainbow with red on top, the violet's coming from a drop lower. Okay? All right. So that's why the red's always on top in the what I call the primary. You can get a secondary rainbow forming, and I don't know if you've ever seen a secondary rainbow. It's extremely faint. It'll be above the primary rainbow, and there the colors are reversed, so violet will be on top. This doesn't show that, but what will happen is some of the light, when it hits right here, right, these rays come down from the TIR, and they hit right here, some of that light energy is going to reflect back into the drop. And if you look at that reflection and then final refraction out, all these drops will form a secondary rainbow. I've only seen a secondary rainbow once. The conditions have to be just perfect, and it's extremely faint, but it's a cool event. And also, if you can do your own rainbow formation, you guys probably have done this, right, with a garden hose. If you put the garden hose on mist and get a lot of fine drops in the air, get the sun behind you, and you can form your own little rainbow. Okay? All right. Rainbow formation is neat, and I encourage you guys to read much more about it. I thought I'd just throw that there. All right, so look, go back to the summary notes. For normal dispersion, index decreases as wavelength increases. Red's going to have a lower index than violet. And for light going from air into a medium, violet bends the most, red the least. Okay? All right, those are the main concepts I want you to remember. That's it for dispersion, and that's it for this video. Bye-bye.